Good morning, everybody. I'm going to show you a neat device that you all need to make. It helps you troubleshoot diodes, integrated circuits, transistors, inductors, capacitors. This box right here does it all, and it connects to an oscilloscope that has the XY function. This will not work with a scope that does not have the XY function, so you need an oscilloscope that has that mode. At the end of the video, I'll show you the schematic diagram so you can build one of these. Today, we're going to test this germanium diode. It's part number 1N34A. Here we have a small signal diode. It's 1N4148. Here's a rectifying diode, part number 1N4007. Here's two Zener diodes. This is a 5.6 volt Zener diode, part number 1N4734. Here's a 10 volt Zener, part number 1N4740. Here is an NPN transistor, part number BC546. And here are two transistor driver array ICs, part numbers M54563P. Now one of them is shorted, and I'm going to show you the waveform that this box displays on the oscilloscope for a short circuit. We'll see all the waveforms for all these devices. These two connectors right here connect to the oscilloscope. Here's the X input that goes to channel 1. That'll be our X-axis waveform across the bottom. Here's the Y-axis input to the oscilloscope. It connects right here on channel 2, and that will be on the Y-axis display right here. We'll plug this in to 120 volts AC. Inside here's a transformer. Turn that on. Let's put our oscilloscope into XY mode. I'll show you a close-up here in a little bit of what this looks like. It takes a little bit of getting scope set up right here. There's a potentiometer right here that increases and decreases the amplitude of the waveform. Now sometimes you have to play with the volts per division. Right here is 1 volt per division. We'll start out right there. We want to get this waveform even between the two ends. Here's our probes. We have a red and black probe. They plug into the magic box right there. Now I'll show you close-ups of the waveforms while I'm explaining where I'm connected here, but to begin with, let me show you what this germanium diode does. What it looks like on the screen. See that? That's a good germanium diode waveform on the oscilloscope. There's open. There's the diode drop. Here's small signal. Here's rectifying. Let me move the camera so y'all can see a better view of the waveform on the oscilloscope. Okay, I'm going to clip onto the germanium diode with some clip leads, and I'll point out some interesting points on the screen. Now notice I've got the scope X and Y set to 1 volt per division, so each one of these is 1 volt. Notice where the breakover point is. It is very close to 0 on the X and Y axis, the origin point. And then it gradually goes out, but it never gets past half a volt, 0.5 volts. We'll go look at the small signal diode now and you'll see the difference. Let me unclip here. Here is the small signal diode. This is the 1M4148. Now notice where the breakover point is. It is closer to half a volt, 0.5. Now that's what you'd see if you set your fluke multimeter to diode test mode and looked across that diode, cathode and anode. You'd see 0.5 or thereabouts on your meter. Isn't that interesting? Let's go look at the 1M4007, the rectifying diode, and clip onto it, and you see it looks very much like the small signal diode. It breaks over, its knee is at about 0.5. Now let's go look at the 5.6 volt Zener. I'll clip onto that. Now I'm going to change the volts per division to 5 volts per division. I'm going to increase the potentiometer on the magic box. Look at that. Look at the magic there. You can see here, this is the Zener point. This is where it Zeners. Here's the origin, and at 5.6 volts, it Zeners. Isn't that amazing? I'm going to move the clips over to the 10 volt Zener diode. Look at that. It Zeners at 10 volts. Here's 5 volts per division. Here's 10 volts per division. And there's the Zener region. Isn't that amazing? Now Zeners are placed in the circuit reverse biased. So you can see another point. This is where it's forward biased. And this, at the Zener region, where it breaks over, is where it's reverse biased. It's amazing. Okay, now we're going to look at that NPN transistor, that BC546. We'll see what the waveforms look like that from the magic box. And we place that lead there. That's pin 2, and I'll place the other lead on pin 1. This is the waveform for base collector. You can see we're at 0 on the y-axis and the other part on the x-axis. that one there. And on pin 2, we'll move the other lead to pin 3. This is the waveform for the base emitter. Now we'll take the one lead off of pin 2, get out of there, and we'll move it over to pin 1. Here is the collector emitter waveform. Here's the origin, and we have a breakover point over here. Let me show you those waveforms I've got drawn out here. Here's the base emitter waveform. Here's the base collector waveform. And here's the collector emitter waveform. Okay, we're going to unclip from that NPN transistor. Now we're going to go over and test the transistor driver array IC, M54563P. We're going to look at a good one first, so we'll have some comparison. Put any lead, red or black, on pin 10. Pin 10 is ground. The only difference is your waveform will be reversed if you reverse the leads. We're going to look at pin 1. That's an input. Okay, notice how the diode drop is diagonal down there on the bottom. That means there's resistance in that circuit. That's pin 1. Must have some resistors going to ground. That's why we're diagonal down there. Here's pin 2. This is an input. 3. Pin 4. Pin 5. Pin 6. Pin 7. Pin 8. This pin right here is the freewheeling diode connection. This is pin 9. That's pure diode right there. Let's go over to the output side. Here's pin 11. That's a good diode drop. Pin 12, this output. 13. Pin 14, pin 15, pin 16, pin 17, an output, and finally, pin 18. That was looking at the good transistor driver array IC. Now let's go look at the bad one. Put your lead on pin 10. Here's pin 1. That looks good. Pin 2. Pin 3. Pin 4, an input. Pin 5. Pin 6. Pin 7. Pin 8. And here's pin 9. The freewheeling diode contact. Straight up and down, that's shorted. Whenever you see a waveform straight up and down like that, that's a short circuit. Let's go over to the output side. Here's pin 11. That's shorted. Pin 12. That's shorted. Pin 13 output. That's shorted. I slipped off of it. That's shorted. Pin 14. Short. 15. Not quite shorted, but it is. You can see where it breaks over, but it's not a perfect diode drop, so something's going on with that one too. Here's 16. The same. 17. That's shorted. 18. And that one too, there's something going on with there. Alright, okay. So now, with this magic box, we've tested diodes, transistors, integrated circuits. That's an amazing box right there. You go make you one of those. Oh, one note I didn't mention about Zener diodes. The amplitude of this box is not very great, and so I don't think it can turn on a Zener greater than 10 volts. So if you're testing Zeners and you don't see it Zener over, it's because the box's amplitude is not that great. You don't want it too great because you'll start popping semiconductors. Okay. You know, let me grab a couple of resistors over here and we'll take a look at those. I'll grab a 1K, a 10K, and a 100K, and we'll look at the waveforms for those guys. Give me a little bit to go scrounge up some resistors. Okay, I'm back. Now here, we're going to look at the 1K resistor waveform. Okay, you can see it's not straight up and down, it's diagonal. The lower the resistance, the more straight up and down that waveform is. That's the 1 kilo ohm resistor. Let's go look at the 10 kilo ohm resistor. Now notice we're becoming more open. It's still diagonal, but it is leaning more towards horizontal. Here's the 100 kilo ohm resistor. Now we're not quite horizontal, but you can see it is very close to horizontal. So the higher the resistance, the more horizontal that waveform becomes. Evening all. Here we are another day. I'm going to show you what's inside that tester. This is very easy to make. It's not hard at all. It takes you a few parts, but they're easy to assemble. Here's the line plug. Here in America, in the house, we have 120 volts AC at the wall socket. This plugs into the wall socket right here. The hot comes in, it goes through a switch to the 100 volt tap on this transformer right here. The other part of the transformer on the primary side goes to the neutral. Here's a switch to turn the unit on and off. Now, I built this tester back in 1998 and I didn't put a fuse in here. I was back in my brave days. I ought to put a fuse in there, but I didn't. So y'all put a fuse in there. I'll put you a fuse holder between the line plug and that switch and put you a fuse in there. Doesn't have to be a large fuse. I'd say half an amp maybe, or less, just to be safe. Now the tester is in a plastic box. if I had this tester in the metal box, I would have frame grounded this thing, but there's no metal that I'm going to get a hold of, so I never hooked up the frame ground pin of the plug. Y'all might want to, but maybe tie it to a screw on the transformer. But I didn't. I wasn't worried about that. Here on the secondary side, I'm coming off of the 12 volt tap on that transformer. I'm running the 12 volt AC into the wing of a 10k ohm potentiometer. The output of that 10 kilo ohm potentiometer goes across this 330 ohm resistor and this 3.3k ohm resistor, and also to the pin of the Y-axis BNC connector. That's this connector right here. The outer ring is ground and the pin is along this line right here. On the 0 volt tap of the secondary of that transformer, we run to the other side of the 330 ohm resistor, and we also go to the red probe banana jack. That wire also goes to the pin of the X-axis BNC connector right here. Now you'll notice that the ground ring of the BNC connectors are connected together, and to the black probe banana jack. That black probe banana jack is also connected to a 3.3 kilo ohm resistor that goes up to the Y-axis and potentiometer wiper wire right here. There you go. That's what's inside that magic box. Now I'll get you close-up pictures of this so it'll be easier for you to see. Be careful on this side over here. If you have 220 volt, 230 volt service in your country, this transformer won't work for you. You have to get a transformer that has the 220 or 230 volt primary. And if you feel worried about it, fuse this. I should have, but doggone, that was a long time ago. I can't think of why I didn't. And if I built this thing today, I'd put a fuse right there. And I'd also take this frame ground to the mounting screw of that transformer, just in case that transformer shorted out. It would pop that fuse right there. Okay, all right. Oh, one more thing. In your country, you got brown and blue wires. They don't mean what you think they mean in your country. Over in Europe, they use brown and blue for DC voltages. I use brown and blue because that's the wire I had in the bin. There wasn't no rhyme or reason for that. It was just the wire colors that I had. All right? Okay. Oh, these resistors right here, they're 1/4 watt. I don't know what wattage that potentiometer is. It's a panel mount pot, so it any panel mount pot of a good size will work. The probes down here, those are the ones you go out and attach to the device you're testing, the diodes and the transistors and resistors, capacitors, inductors, whatever you're testing with this magic box right here. You look at them with these probes right here. These BNC connectors, they attach to the oscilloscope that you put into XY mode. Your oscilloscope has to have an XY mode function so that you can see the trace waveforms of the diodes and transistors and whatnot. I'm going to try, I don't know if I can, but I'm going to try and show you what's inside this box right here. I just dropped my pencil. Yeah, I ain't trying too good. So here's the transformer that takes the 120 volts AC and converts it down to 12 volts AC. Here's the potentiometer right here. Here's the BNC connectors. There's the red one. Here's the black one. Here's the coaxial cable that's connected to these BNC connectors. There's the X-axis connector, and there's the Y-axis connector. Now you see that? Do you see this shield right here? The shield is that ground right there that goes to the black probe. You can see that the shield is connected to the black probe banana jack, and that shield is connected to the barrel of the BNC connector right there. Now the pins of the BNC connectors are right here. Now you'll notice one of them goes to the red banana jack, that's the X-axis, and the other one goes to the potentiometer and the 2 quarter-watt resistors. That's this one right here. Okay, I hope I've explained this enough to where you can put that circuit together. Okay. Sometimes I get a little bit long-winded there, and I explain things into too much detail to where it gets a little bit confusing. But with the diagram there, it ought to be easy to build. I hope so. Go build you one of them. You'll have a lot of fun with that, looking at diodes and transistors and resistors and whatnot on your oscilloscope. Okay, now really I'm going to get out of here this time. Okay, good night folks. We'll see you next time.